Hey, hello everyone. Good. Today we will have the upper last topic for CS1, and it will take maybe 1 hour, so we'll finish late earlier. Um, so the topic for today is binary trees. And after Thanksgiving, the last topic will be hash functions and hash tables. So binary tree, the tree data structure is typically represent a tree, but with root on the top. So here's the example of the tree. Binary, it's called binary because every node may have up to 2 children. Some nodes don't have children at all. We call these nodes leaves. They have just one child. And the root doesn't have parents, the root node. Why we actually are interested in this data structure? The answer is that if you will, okay, I didn't mention the difference between binary trees and binary search trees. So in binary trees, the values in the nodes can be arbitrary. In binary search trees, if you take any node, the values for nodes to the left are always smaller than any value to the right. So this representation is convenient because if you will print these values, they will be printed in sorted order. So this data structure is sorted by construction. So it's zero time complexity for sorting. Okay. We will talk about these problems, how to create this data structure, how to print the values of this data structure in a list or in a string, how to search an element in this binary tree, and what is the time complexity. So again, this is a binary tree, but not a binary search tree. So I don't know if this question will be on the final exam. For example, is it a binary search tree? The answer is not, because for example, for this node, we have values in the left side greater than values in the right side. But it's a binary tree in general. So the definition of the binary search tree is recursive. So the empty tree by default is the binary search tree. Then, if we look at the left subtree and the right subtree, if the left subtree is a binary search tree and the right subtree is a binary search tree, uh, we are not guaranteed that our original tree is a binary search tree. There should be one extra condition satisfied, that all the values in the left subtree are smaller than any value in the right subtree. In this case, it will be binary search tree. So let's answer the question, which binary tree is binary search tree and which is not. So what about the first one? Does it satisfy the condition that if we take any node, the greater values will be to the right? Yeah, so the first is a binary search tree. The second tree, there should be one node. You can think about, for example, value 61. So if there is a value 61, then this tree won't be a binary search tree, because to the left we will have value 63, and to the right we will have value 61. So it won't satisfy the definition. So terminology, the leaf is the node without children. The child is the subtree of another node, and the node that has at least one child is called parent node for this subtree. Root is the node without parents, the beginning node. And balanced, unbalanced, we will talk about this later when we introduce the notion of the height or depth of the tree. So some definitions. The size of tree is the number of nodes. So what is the size, for example, of this tree? The size is just the number of nodes, 9. Okay. The height is the, for depth, is the length of the longest path. So, for example, if we have this tree the other name for the tree of depth 1 is stump. So stump is the tree of depth or height. We use these words interchangeably. Tree of depth 1. So if we consider just this part of our tree, this tree will have height or depth 1. If we consider the next level, this tree will have height 2, and finally the entire tree will have the height 3. So the formal definition is that the depth of the tree is the number of edges in the longest path. So this is the longest path, and the number of edges is 3 in this path. So this is the definition of the depth of the tree. And balanced tree So the tree is called balanced if the height of left subtree is the same as the height of the right subtree. This tree is unbalanced because the heights are different, and the difference between the heights is called imbalance. So what is the imbalance of this tree? 1, because the height of this tree is 2, the height of this tree is 3, so the difference is 1. Okay, so now let's create this data structure. For every node, we'll have the value and the left child and the right child. The values can be none or a subtree. So for example, the empty tree will be just none. The one node, just the tree of depth 0, will be represented by this data structure value and nuns for subtrees. And the tree that I drawn earlier will be represented as this data structure value 3 and 2 subtrees. So last time we were working with linked lists. And as you remember, in linked lists, we had also value and link to the next and previous. And we applied recursion because we applied some operations also to the next and previous list nodes. The same will be with binary trees. The base case will be when we reach the leaf node, the terminal node without children. And if it's not the leaf node, we will apply our function to subtrees, to the left and right subtrees. So this is the general pattern for our functions. So something new for today, how to check if the node is none. We can just write if tree.value is none or equals none, or we can use this fancy function isInstance. So in Python, as you remember, everything is a class. And for example, when we create an integer, then it has the data type of class int. And we say that 5 is the instance of this class. If we create a string, then we create an instance of the class string. When you created your user type node, you first defined the type, and then you created the object, the instance of this type. So there is a function that checks that your variable is of the specific data type, is instance of the specific class. For example, if we check that this list is the instance of your class binary tree, you will get false because the list is not the binary tree. If you check if your list is the instance of class list, you will get true. So we will use this function today to write our first function that will calculate the depth of the tree. So week 13. So we will create user data class binary tree with parameters value and left and right. Left will be of type none if there is no left subtree, or the binary tree. Value will be any, and right will be also of type none or binary tree. So let's create our objects of this type. Oh, sorry, I had to import any, not all. Tree 1 will be binary tree with values 1, 3, and 4. So 3 will be the parent node, 1 will be the left subtree, and 4 will be the right subtree. So if I print it, it will print this stump binary, the tree of size 3 and depth 1. But it's very hard to read, so we will write the second function we write today will be to print the values in a line. But the first function will be just to calculate the depth. So let's create function for height of tree. And as I mentioned before, we will use the recursion. The base case will be applied to the node with empty subtrees. So if and here I will use this fancy function instead of writing if tree equals none, I will type if not is instance tree of binary tree. So if my tree is none, then is instance will return false. For example, I will show this now. If is instance of tree binary tree will return true, but if I'm using none here, it will return false. So if I want to check that my tree is actually empty tree, none, this value will return false. So I'm using not is instance to get true. So if it's so if my tree is none, I will return something, and otherwise I will increase my depth by 1 and look at the depth of left and right subtrees. I will take the maximum of the heights of the tree left and height of tree right. Height of tree right. So the only thing remains what we will return. So every time we look at the trees, look at the subtrees, we will get a tree of height smaller at least by 1. So here I will add 1. So I add 1 edge and look at the subtree. So it will be, the height will be smaller by 1. I will add 1. And here for the tree of depth 0, so it will be wrong, but for now I will return 0. And let's print the result. Height of the tree. As you remember, the height of my tree with 3 numbers is 1, but I've got 2. To fix that, for empty node, we should return -1. So it will fix our problem, because here we add 1 even for the parent node, for the root. If we add -1, then we will get the correct depth. Okay. Next function, as I said, is to print the values. So for this tree with 3 values, it should print the values 1, 3, and 4. There are some test cases, but I will skip this. If you upload code from course page, there will be test cases like for empty tree, for tree without 1 subtree, and so on. So we will use our pattern for recursion. And if our tree is empty, what should we return if we want to print a string of values? If our tree is empty, we will return empty string. So here is the code. Without fancy is instance, here I use tree is none, but it's the same. And we return empty string. If it's not empty, we print the value and concatenate with all the values from the left and all the values from the right. So let's implement this function. So it will be binary search tree to string. So base case, if node is instance tree of binary tree, return empty string. Else, we can write else, but because there is return statement, if we go in this branch, we actually will finish the execution of our function with return statement. So we can write our code without else, even though here we have else statement, but the performance will be exactly the same. Return. So we will print the values from the left subtree. Then we will add empty string and print the current value, tree dot value. And then again, empty string. Oh, not empty, but the space. And finally, the right subtree. And I have forgotten to cast the value into string. If it's integer, it will be cast into string. Okay, now let's run our function. And you can see that it prints the values correctly. So I don't think we need to do a break because we will finish earlier. But if you need to go to bathroom, you're welcome to. So here's the substitution trace for this function, recursive function. We print the value 3 and apply our function to left and right subtrees. Left and right subtrees contains of just one node. So we print the value of this node and apply our function to left and right subtrees of that node, which is none. And when it's none, it prints the empty string. This is how it works. So yeah, here I typically would make a break because now we will go to the next topic, which is called traversal of the trees. There are three ways to go through our tree, and it will be on the final exam, so you should be familiar with these three traversals. But let me erase my writings. Okay. The drawings. Oh, it looks like I saved them. Okay. So okay, we can just go through these errors. The first traversal is called in order. So first we go to the left node, then parent, and then right. So here's the example. We begin with a root, and then we go to the left. Now we consider this node as a root, and we again go to the left. So in order, we go to the most left node first. And it will be, the value will be 1. Then we go to the parent node of this node, and we will get number 3. And then we go to the right of this parent. After that, we visited left subtree. Now we go to the parent. The parent of this subtree was our root. So we will print 5. Now we visited our left subtree and parent node. We will go to the right subtree. Right subtree. Now this is our root. So we go to the left first, and we will return 6. After that, we go to the parent node 7, and finally we go to the right. And as you can see in the result, we have all numbers sorted in order. So that's why this traversal is called in order. And next traversal is called pre-order. So the difference is that we begin with parent node and then left and right. So we begin with root, and because the first step is parent, we print the parent value 5. Then we go to the left subtree. Now this is our root. And we apply again this rule, the parent. So we print 3 and go to the left subtree. The left subtree is the leaf node. It doesn't have children, it's parents. So we print 1. And after that, we go to the right subtree. Right subtree is 4. So we visited our left subtree. Now we go to the right subtree. So we go to the right subtree of our original node. And consider this as the root. And our rule says first parent node, so we print 7, then left subtree, then right subtree. And finally, the third traversal is called post order, where we begin with left subtree, then right subtree, and only after that, the parent node. So first we go to the left subtree. Then we consider this as the root. Then we again go to the left subtree. So again, we go to the most left node. And then to the right. So after 1, we will get 4. And then to the parent. After we printed 3, we go to the right. And in this node, we go to the left. Left, again, right, and finally parent. When we visited the right subtree, we go to the parent. So 5 will be the last number. So now let's practice with you to print the values of our tree in this with these 3 different traversal modes. So the first will be pre-order. Parent left, right. So if we begin with root node, what we will print first? If we follow this pattern, parent left, right.
No,
What?
because you're going to be in on the left of these.
No. If we begin with pre-order. So first we will print parent, then left, then right.
Oh, okay.
Yeah, the first.
I thought you will go down the left and print the first.
No, the first node for pre-order will be parent A. What will be the next one? We go left subtree, and in left subtree, we follow the same pattern. So in the left subtree, we should print parent. So what will be the next node after it? B, because for this subtree, B will be parent. So then we follow this pattern. After parent, we go to the left, but left is empty. So we visited left, we go to the right. So the next node will be D. So here is the complete traversal. So parent, again left, again parent, left, right. Then we go to the, we visit the entire left tree, we go to the right, then parent, C, left, and its parent, so we print. Again left, its parent, again we print. Then right, F is parent, then left, right. For in order, we just print all the nodes from left to right. So it will be B, D, A, G, E, C, H, F, I. And for post order, we visit first the left subtree, right, and then parent. So we go to the left subtree. Then we should go to the left subtree, but the left is none. Then we go to the right subtree, it will be D. And then we go to the parent, it will be B. After that, we go to the right subtree. In right subtree, we go to the left, so it will be G. Then to the right, it will be none. And then to parent, it will be B. Then to the right, left, so it will be H. Right, parent, parent, parent. Okay, and the last code for today is searching. So how to answer the question if an element is among our nodes? Okay. So we will write, actually we won't write because we will just look at this function. This function takes two values, the tree and the element. And it should return true if the element belongs to our tree and false if it's not. Again, we should consider test cases. And we will follow the same pattern. If our tree is empty, we will return false, because if it's empty, then any element won't belong to our tree. But let's answer this question. Is it possible that we will have the element in both and right and left subtrees? So you remember the definition of the binary search tree says that all the elements to the left of the node should be smaller than any element to the right. So it means that we can't have the same elements from the both sides, because these elements should be smaller than those. And it will help us to find the element, because if the element, the value of interest, will be smaller than the current value, then we'll continue search only in the left side. Does it make sense? If the element is smaller than the current value, then we will search only in the left subtree. If it's greater, we will continue search only in the right subtree. And here is the final code. If our tree is empty, false. If the element is smaller, we continue search in left subtree. If it's greater, we continue search in right subtree. And if it's equals, we return true. Yes.
So it's basically just binary search.
Yeah, it's kind of. And we will talk now about complexity, and you will see it's the same time complexity. Did you have a question?
Are duplicates allowed in binary search trees?
Sorry?
Are duplicates allowed in binary search trees?
Oh, we don't allow duplicates. By our definition, it's impossible to have like the same values to the right or to the left. So, but you can think about binary trees with duplicates. So I won't write this code. Let's just look at the substitution trace. So we are looking for the element 1 because it's smaller than 3. We continue our search in the left subtree. And it coincides with the value of the left subtree, so we return true. Now let's talk about time complexity. So 2 slides left, time complexity and list representation. So this is about your comment about the binary search. So consider 2 cases separately. One case will be balanced tree. It means that left and right subtrees have the same length. If our tree is balanced, then if we have n elements in each half, we will have approximately n over 2 elements. Or maybe plus 1 if it's not even. So for balanced tree, for each subtree, we will have twice smaller elements in each subtree. For the next level, we will have again twice smaller elements. So every time we will have n over 2 power k elements. I will write it down. So for level k, we will have n over 2 power k elements in the subtree. And for the last node without children, the leaf, we will have only 1 element in this tree. So we will stop when the number of elements in subtree is 1. And do you remember we solved this equation? The solution was k equals log base 2 of n. So the time complexity for searching, and you remember for searching, we always choose right or left subtree. And it means that we go kind of by the level down to the tree smaller by 1. So the maximal number of levels will be log of n. So this is for balanced tree. I've taken this picture from internet, and you can see here another logarithm. What stands LG for? Huh?
Isn't it just log?
Log, but what is the base?
Base 10?
Base 10, yes. Because there's specific names for log base E, ln, and log base 10 is lg. So why it doesn't matter which base we are taking. So this is the same as log base 10. This is natural log. Because there is a formula how to change the base of the log. So for example, log base C of n is equal to log base 2 of n over log base 2 of C. So it means that if we take like log base 10, it will be proportional to log base 2, and the factor will be 1 over log base 2 of 10. So it will be just a constant. And as you remember, so it will be just a factor. And as you remember, the time complexity O of n or O of 2n is the same. Or if we look at the O of 4n, so it's up to the factor. So the time complexity of log base 10 will be the same as the time complexity of log base 2. Because the difference is just up to the factor 1 over log base 2 of 10. So that's why you can see natural log, you can see log of base 10, you can see log base 2, but they will have the same scale. Okay, now let's consider unbalanced tree. So, for example, I have, I will clean this. So, for example, I have 5 elements with elements 1, 2, 3, 4, 5. And I create this tree. 1, 2, 3, 4, 5. And I create another tree. 1, 2, 3, 4, and 5. I hope you agree that both trees are binary search trees. Because if we take any node, the nodes to the left will be smaller than nodes to the right. But the depth of the first tree is 2, the depth of the second tree is 4. So what will be the time complexity? So this tree is balanced, and the time complexity, as we just proved now, will be log of n. But what will be the time complexity in the worst case? It will be n, just the number of nodes. So yeah, in the worst case, it will be linear. And you remember that linear function is higher than the log function. So to wrap up this topic, I want to build a tree. So could you just give me some numbers and I will build a tree. So you will understand how we create the binary search tree. So just give me some integer numbers, for example. Okay, so this will be the root of my tree, 10. Okay. Just give me any numbers. 7 will go to the right or to the left? Yeah, it will go to the left because it should be smaller. Okay. 22 will go to the right. So,
-5.
well, it's easy. It will go to the left of 7. One, where I should put 1?
Second branch off of 7.
Huh?
Off of 9.
Yeah, I believe it will be the right of -5 because it should be greater than -5 but smaller than 7. 8, well, it's easy, Alex. It will go just to the right of 7. 12. 12 will go to the left of 22 because it's smaller than 22 but greater than 10. What? 11. It will go to the left of 12 because it's greater than 10 but smaller than 12. So I think you get the idea how we can build this tree. And in that example, the numbers appeared in the increasing order, so that's why I got this like long tree skills to the right. So the last slide, I'm not sure if we will test this. Okay. Yes, I need your help because my pointer again disappeared. And typically when you come just close it, it appears. Oh, it's here. Thank you. Um, so let's clear all drawings. So this is time complexity for balanced tree and unbalanced tree. And the last slide is about representation of this data structure using Python lists. Instead of our users' data types, you can represent a binary tree. And I believe you noticed it's not a binary search tree, it's a general binary tree because 8 is greater than 7. So you can represent any binary tree with a list. So you start with root, then yeah, it's the end of lecture. Yeah. So then you print the children of this node 8 and 7. Then you print the children of the left node. Then you print the children of the right node, and so on. So this is how you can represent binary search tree with Python list. Instead of like our user data types. Okay, so now it's time for quiz, and and we go to sleep. Um,